A very good morning and welcome to this course on the foundations of continuum mechanics. Today we'll be talking about the topic on plane stress. So let us get started. So the topics for today's discussion are as follows. We'll be talking about plane stress to start with, which will cover most of the lecture today. Then we'll talk about splitting the stress tensor into its spherical part and the deviatoric parts. And finally, we'll end the lecture with a discussion on octahedral shear stress. So let us discuss plane stress first. So plane stress is a situation when one and only one principal stress values is zero. So in this situation, the body is said to be in a state of plane stress. So let us say we have a body and the point P on the surface here is unloaded. So the meaning of unloaded is that there is no force or load acting on the point P on the surface of the body here. So if I was to draw a small area with an outward normal n hat like this, then I would say that the traction on this surface with a normal n hat is 0. That's on point P because there is no external load acting on point P. So the surface force acting on point P has to be 0. And this basically implies that there is no normal stress and no shear stress at point P on the surface. Now, in this case, the surface we're talking about is not a hypothetical surface. It is an actual periphery of the body because the point P lies on the surface. So this plane that we have drawn here is an actual plane with an outward normal n hat depicting the actual surface of the body. So in this situation, we call this surface as the unloaded surface or the free surface. So let us recap our definition of a principal plane. So this is a plane where there is no shear stress. So what that would mean is that the traction vector on this surface with an outward normal n hat will simply be some quantity times n hat. So this is basically saying that the traction vector is along the n hat direction, and that is what is the meaning of a body being in principal stress state. So this value that we get here, if you recall, is called the principal stress. And n hat is called the principal direction. So this is from earlier discussion. Now let's look at this situation. So we have a point P with an outward normal n hat, and the traction vector in this case is a 0. So we can substitute a 0 here, and this satisfies the discussion of a principal plane. So this is a very special principal plane where the principal stress value is a 0, as we just discussed. So for discussion today, what we'll do is we will call this principal stress value as sigma 3, which is equal to 0 here, and the principal direction corresponding to it becomes an n hat with a superscript bracket 3. Remember, we designated the principal stress values as sigma 1, sigma 2, and sigma 3. So we're just saying that this value that we have gotten here, which is a 0 on this plane, the unloaded plane, let's call this sigma 3. This is purely for discussion. So this n hat is an n hat 3 here. And by the way, this plane that we have, which is the plane on which there is no loading, is called the designated plane. So this is terminology. So since we know that the three principal stress directions are mutually perpendicular to each other. So that means n1 hat and n2 hat will lie in the designated plane. So for discussion today, we will choose an axis px1, x2, x3 passing through P with P as the origin in such a way that x3 direction coincides with n3 hat direction. So what that will mean is that this becomes our x3 direction, and the other two directions x1 and x2, which as you can see will lie in the designated plane, can be chosen arbitrarily for the discussion right now. So I've shown just one choice of x1 and x2 directions which lie in the designated plane, but they may not necessarily coincide with the principal directions as of now. So this results in a 3D right-handed Cartesian coordinate system, which is Px1, x2, x3 in this case. Now what we'll do is we'll write the Cauchy stress tensor in this chosen coordinate system. So here's our Cauchy stress tensor with the 9 components, and we know that the third row of the Cauchy stress tensor is nothing but the traction vector on E3 hat in this coordinate system. But we already know that since E3 hat coincides with N3 hat in this case, so this is a 0. So this basically means that all the 3 components of that have to be 0, and this will result in the condition that sigma 31 equals sigma 32 equals sigma 33 are all 3 zeros. And since sigma is a symmetric tensor, we can write sigma 13 and sigma 23 are also zeros. So this results in a simplified situation where the Cauchy stress tensor sigma becomes. So you may notice here that this representation of sigma looks like a 2D situation. Now I make this statement in a very hand-wavy sense, in a way that this is not a 2D situation completely, because they'll be cutting planes with normals outside the designated plane where the stress tensor will have or may have all 9 non-zero components. But just looking at sigma in this situation, you may see that it's like a 2D matrix with the 4 components sigma 11, sigma 12, sigma 21 and sigma 22. So it's as if all the interesting stuff is happening in a plane, and hence the name plane stress situation. Now let us draw the cube picture of the situation. So in this cube picture, where we represent the various cutting plane as separate planes, although ideally they are all passing through the point P. So this is the surface with even hat normal, and if I go back up and have a look at the stress here, I can see that the first row of this is simply sigma 11 and sigma 12. So that basically means that I have a normal component of traction here, which is sigma 11, and I have a component along the E2 hat direction, which is sigma 12. So there's no sigma 13 because of the reason that sigma is symmetric, so sigma 31 and sigma 13 both were 0. Now we'll see the cutting plane with an outward normal in the E2 hat direction. So here again the second row of sigma on the top right shows that there is a normal component which is sigma 22, and there's a component along E1 hat direction, which is sigma 2, 1. And these are the only stresses acting, because on the third E3 hat plane, there is no loading, hence there is no sigma component. So we can see that on any plane, we have a sigma n and a sigma s, where the sigma n is given as, let's say, sigma 1, 1, and sigma s is given as sigma 1, 2 on the E1 hat plane. On the E2 hat plane, we have a sigma n equal to sigma 2, 2, and a sigma s, which is sigma 2, 1, which is the same as sigma 1, 2. It's a very simple situation, but this situation is happening because we have chosen our coordinate system px1, x2, x3 in such a way that x3 coincides with the principal direction where the principal value is 0. That is the direction of the plane on which there is no loading. If I was to actually write things in the principal coordinate system, that is, if I was to identify x1 star and x2 star as the two eigen directions in the x1, x2 designated plane, well, x3 star coincides with x3 because we've chosen x3 in such a way. So now I can draw the Moore's circles. So we have one of the principal values as 0, which we call sigma 3. And then let's say another principal value is sigma 2, and the third one is sigma 1. So this allows me to draw the Moore circles, and as usual, I'll just draw one half of them, the top half. So these are the three Moore circles, and this is our feasible stress region. And this top part here is where you have sigma s max in this plane stress situation. Sometimes, for simplicity, we just draw the Moore circle which is corresponding to the two non-zero eigenvalues, that is just this one. So here we have sigma 1 as the largest eigenvalue, and then we have sigma 2, and then the third one, sigma 3, is a 0. So we draw just one circle here. This is our principal coordinate system. So if I had a normal along the x1 star direction, that is, I had the cutting plane, which is x2 star and x3 star plane, then on the stress plane on the left, the point that we'll get will, let's call this A here, and the corresponding point A is capital A on the right. Now, if my cutting plane was oriented with a normal along x2 star direction, let's call this B. So please recall that I'm plotting points on the physical plane on the right in such a way that you have the first octant of a sphere, and the normal simply cuts through that octant, resulting in this point capital A or capital B. So the point corresponding to capital B will be the point here, because this is the point which corresponds to the principal value sigma 2. And as I move from A to B, that is, as my cutting planes rotate so that the normal rotates from capital A to capital B, I cover a total of 180 degrees on the Moore circle in the stress plane like this. So we have discussed that a 90-degree movement of the normal in the physical plane is a 180-degree movement on the circle in the stress plane. Now if I choose my x1 and x2 directions so that they don't coincide with the principal directions, but they still are in the designated plane as discussed earlier. So these x1 and x2 will be plotted as these points. So this is point corresponding to where the normal in the direction of x1 cuts the octant. So let's call this R. So this R corresponds to this small r in the stress plane, and the normal cuts the octant at the point S in the physical plane along x2 direction, and that S is 90 degrees to the direction R in the physical plane. So on the stress plane it has to be 180 degrees. So that's diametrically opposite here in the stress plane. Now to figure out the coordinates, that is sigma n comma sigma s for these 2 points, that's easy. If I go back to my cube picture, which was drawn for some arbitrary x1 and x2 directions, we notice that the normal stress was sigma 1 1 and the shear stress was sigma 1 2. So with the same logic, for R, normal stress is sigma 1 1 because R corresponds to x1 direction, and for S the normal stress is sigma 2 2 because S corresponds to x2 direction. In the shear stress is the same magnitude sigma 1 2, but we can see from this stress plane that for point S the shear stress is negative because we are below the sigma n direction, so this becomes a minus sigma 1 2. Now we can easily write the equation of the Mohr circle, this single circle that we're interested in here, sigma n minus something squared plus sigma s minus something squared equal to some radius squared. We'll try to fill these blanks here now. So if you try to locate the center point of the circle, you can easily see that the coordinates of point R and S, especially the sigma n values, if you take an average of that, you get the center of the circle because R and S are symmetrically located around the center. So this becomes sigma 1 1 plus sigma 2 2 upon 2, and this is square of that. Now in terms of center coordinate in sigma s axis, that's a 0, so that's very easy to write. So this becomes sigma s minus 0, so that's basically a sigma s squared. And now for the radius, we have the coordinates of points R and S. So using coordinate geometry, I can very easily find the distance between these two and then divide that by 2 to get the radius. So the distance between 2 points is their first coordinate minus the first coordinate of the other one squared plus the second coordinate of the first one minus second coordinate squared, and this is the square of the diameter, so we take an under root of that, so we get the diameter, and we divide all of that by 2, we get the radius. But we're interested in the square of R, so there's a square here. So I can simplify this. So this simplifies to sigma 1 1 minus sigma 2 2 by 2 squared plus sigma 1 2 squared. Now please remember that while we're discussing just one circle, when we move on the circle, we stay on the designated plane, that is the plane x1 x2 or x1 star x2 star plane. Now there is no reason for us to stay in that plane. Of course, our cutting planes can be oriented in such a way that their normal n hat may not be in the designated plane. So if I rotate my plane in such a way so that the normal goes out of this x1, x2 plane, then I will get a picture which is depicted using this complete 3 more circles in the feasible stress region, and then we can find sigma n comma sigma s in the feasible stress region. So in the plane stress situation, we're just figuring out what happens if our cutting plane is oriented in such a way so that its normal lies in the designated plane. So when you learn more about specific situations with real materials, this will make more sense. But given that this course is on the foundations of continuum mechanics, our aim is to focus on the physical and the mathematical aspects of the plane stress situation. Let's do an exercise where we have an x1, x2, x3 coordinate system. Again, x3 coincides with our n3 hat, that is the direction of the normal where there is no loading, and we find another coordinate system which is x1 prime, x2 prime, x3 prime. In this way, by simply rotating the coordinate system around x3 by an angle theta, again x1 prime, x2 prime, x3 prime may not coincide with the starred coordinate system here. It may or may not, but this is a general case. So if I write the transformation matrix for this case, I can see that x1 prime makes an angle of theta with x1. So this becomes a cos theta. Then you have a sine theta, and this is 0. And then x2 prime makes an angle of theta with x2. So this is also a cos theta. And this becomes a minus sine theta. These are zeros. x3 prime makes an angle of 90 degrees with x1 and x2, but it makes an angle of 0 degrees, so this is a 1. So with this knowledge, I can find my sigma prime, that is the 9 components of sigma prime, as A sigma A transpose, where sigma is the representation in the px1, x2, x3 coordinate system. That's a black one. And when you substitute the 9 components of sigma in the form that we had written, where only 4 components were non-zero, and the expression for A and A transpose, you get this expression for sigma prime. Now think about it. Why have we only written these 3 components of sigma prime? What about the other components? Let's see what sigma prime would look like. But the direction x3 prime coincides with x3, which is actually the principal direction where there's no loading. So these components will become 0 as earlier. So we have only 4 non-zero components in sigma prime as well, where it's symmetric. So sigma prime 1, 2 is the same as sigma prime 2, 1. So we only need to specify these 3 values. And if you had chosen the prime coordinate system coinciding with the starred coordinate system, that is theta rotation corresponding to the situation where you ended up getting x1 star, x2 star, and x3 star, then our sigma 1, 2 prime would become a 0, and sigma prime 1, 1 would become a sigma bracket 1, and sigma prime 2, 2 would become a sigma prime bracket 2. So in that situation, we can write sigma 1 as this expression and sigma 2 as this expression, where the sign changes to a negative and both terms remain the same. So it's worth looking at it from a geometrical picture as well. So let's do that. So this was sigma 1, this was sigma 2, and let's label the axis as well. And we had drawn a point R which corresponded to the normal in the x1 direction. and then diametrically opposite we had a point S, which corresponded to the x2 direction, and the coordinates in the stress plane for R were sigma 11 comma sigma 12, and for S they were sigma 22 comma negative of sigma 12. So what is sigma 1? Sigma 1 is this one. So if I was to think geometrically, then sigma 1 is the coordinate of the center plus this distance. And if you look at the expression for sigma 1, this is the coordinate of the center, or the sigma n coordinate of the center. This is sigma 11 plus sigma 22 by 2. That's the average of R and S. And then this distance that you have is simply the radius of the circle, which we had found out earlier as this expression. Similarly, if I have to find sigma 2, which is symmetrically on the left of the center, that's the same quantity minus the radius. So this is where having a geometrical picture like Moore's circles is very useful when identifying the sigma n and sigma s values or principal values and so on. So it's always recommended that for a given situation, if you can, you draw the Moore circles. Even if you cannot find the values, just to visualize things, it is always helpful. So before we move on to the next topic for today's lecture, let's solve an exercise. And we can see from here that one of the directions is a principal direction, which is a plane stress situation, that is, there is no loading. And in the other two directions, there is equal tensile and shear stress, that is sigma naught, on both planes x1 and x2. So to find the Moore circles, the thing we need is the three principal values. So we will solve the eigenvalue problem for this. So after solving the eigenvalue problem, we get these three principal values, which means that sigma star looks like this, where you have a 2 sigma naught here, and then the other two principal values are 0, and of course the other components are also zeros in sigma star. In fact, this case is a special case of the plane stress situation because we have two principal stress values 0 instead of 1, and this situation is called a uniaxial stress situation. So if I was looking at the body in the principal coordinate system, it would appear that all I have is a situation where I'm applying a tensile stress in one direction only. That is, if you take a body and apply a tensile stress by just pulling the body in one direction, that would be a uniaxial state of stress. So let's draw the Moore's circles for this case. So in this case, we have sigma 1, that is equal to twice sigma naught, but the other two principal values are zeros. I'll write sigma 2 equals sigma 3 equals 0, and our circle looks something like this. Of course, I've drawn just one half of it, which is good enough. So from here I can see that my sigma n max is equal to twice sigma naught, my sigma n min is 0, and my sigma s max is sigma naught. And if I also had to locate the normal n hat for the cutting plane, which corresponds to the maximum shear stress in this case, then we can see that if I move on this circle like this, I'm basically going from sigma 1 to sigma 2. So let's look at what sigma 1 and sigma 2 denote in terms of the physical plane. So if I had my normal oriented along the x1 star direction, I would get this point. Let's call this small a. This is capital A. And if I had my normal oriented along x2 star, that will be the point B, which is this point here. So a 180-degree movement in the stress plane is a 90-degree movement. So a 90-degree movement in the stress plane here to go from point A to the point, let's call this E, which corresponds to the sigma s max, that will be a 45-degree angle like this. So this n hat corresponds to sigma s max. Now, but you may also say that sigma 3 also is here. So if I was to call this point C as well, but point C corresponds to sigma 3, so that would be point here on the x3 star direction. So by that logic, if I am moving on the circle from small a to small c, then small e lies somewhere between capital A and capital C on the right hand side. So that will correspond to a normal in this direction, which also is corresponding to sigma s max. So on these two cutting planes, your sigma s would be maximum, which is equal to sigma naught. So again, Moore's circles give us a lot of information that otherwise would be difficult to get analytically. So we also noticed here that there was only one circle, because since sigma 2 and sigma 3 are equal, so that circle which was between sigma 2 and sigma 3, it degenerated into a point. And the circle which was between sigma 2 and sigma 1 and sigma 3 and sigma 1 both coincide. So in this uniaxial loading situation, we only have one circle to show. We now move to the next topic, which is on spherical and deviatoric stress components. So we write sigma ij as a sum of alpha ij and sij. It's a standard thing to do, where alpha ij is called the spherical stress. Remember, sigma ij is the complete Cauchy stress tensor, and Sij is called the deviatoric stress, or sometimes just the deviator. Now, although we are doing this for the stress tensor sigma, but we can do this split on any tensor. That is, we split it into a spherical part and a deviatoric part. So let's talk about the spherical part first. So if I write the word spherical, this denotes some sort of a symmetry in all directions. If I write the word isotropic, which we discussed in the mathematics discussion, then that also means directional symmetry. Additionally, if I have a stress tensor where all directions are eigendirections, that means that sigma 1, sigma 2, and sigma 3 are the same. So that is a situation where I have all n hats are eigendirections. So these three ideas are all the same. So let's look at the last one, where we say that all directions are eigendirections. This basically means that the spherical stress tensor alpha ej is an isotropic tensor, which also means that all directions n hats are eigendirections, because for an isotropic tensor, all three eigenvalues are the same. So I can write an isotropic tensor delta Ej as 1, 1, 1, and the spherical part would be some constant times this value, because any scalar multiple of an isotropic tensor delta Ej is also an isotropic tensor, as we have seen in the past. And I leave it to you to figure out or to check that if you multiply this alpha ej with any n hat, you end up getting the same n hat with multiplied by the constant c. So we represent alpha ej as sigma m times delta ej, where sigma m is that constant we just talked about, and the sigma m is given as 1/3 of the trace of the Cauchy stress tensor sigma, and this is called the mean normal stress. Let me give you an example. This will help you appreciate the idea of spherical stress better. Let's take a situation of fluid statics. That is, you have some water, so to say, in a vessel, and deep down below, you have a surface, solid surface, like this, and you want to find out the force on this top surface of the solid, this one. Now, we have been doing this for a very long time, and we say that the force acting on this surface is going to be normal to the surface because of the pressure or the static pressure in the fluid or the hydrostatic pressure in the fluid. So I can write the force F as a force magnitude, which is simply the pressure of the fluid at that point times the area of the surface, and the direction is opposite to the normal, outward normal, so that's a minus n hat. And this is true for all normal directions, because if I had a surface oriented in a different way like this, then the force would be in this direction. So pressure always applies a force which is normal to the surface. This is something we know as well. So let's express this as minus P naught times A times n hat. So what's the traction here? Well, the traction is simply minus P naught times n hat, because when you multiply the traction by the area A, you get the force. So this is true for all n hats. That's very important. And if you look at this situation, this is a situation of eigenvalue problem, because your traction is acting along n hat, and that is only true when you have a purely normal stress situation. So if I was to write my traction as sigma ij nj, and this is minus p times ni, this means my stress tensor sigma is simply minus p naught times delta ej. And this is an isotropic tensor. So what that means is it's a purely spherical stress. It's directionally symmetric. That is, pressure will apply force which is the same on any area in the normal direction always. So this is a classic example of a spherical state of stress. And it's a very important idea as well, because if you think of the design of submarines, which is an engineering marvel, so it took a lot of time to excel, because the pressure applies a force which tries to squish the submarine, And as you go deeper and deeper, the pressure of the fluid increases, and this required the engineers to ensure that the surface was strong enough to resist the compression, which was in a way trying to compress the body, that is, trying to decrease its volume. Now we write the other part, that is a deviatoric part. So deviatoric stress is simply defined as sigma ij minus 1/3 sigma kk, that's the mean normal stress, times delta ij. So we have subtracted alpha ej from sigma ij to get Sij. And if I apply contraction on this, let's check that. If I do Sii, that becomes sigma ii minus 1/3 sigma kk times delta ii. Now delta ii is a 3, so this 3 and this 3 cancel, and this becomes sigma ii minus sigma kk, which is a 0. So this is a definition of the deviatoric stress, that the trace of a deviatoric stress is always 0. Sometimes we define the deviatoric stress this way, that it has the 0 trace or it has no isotropic part contained in it. So that means the first invariant of S is a 0, and the other invariants of S, the deviatoric stress, are half times Sii Skk, the standard way we write the second invariant. But we know that the first invariant is 0, so this simply becomes a minus half Sij Sji. But if sigma is symmetric, so is S. So Sij Sji can also be written as Sij Sij. And the third invariant is simply the determinant of S. So let's try to understand the relationship between the principal stress values and principal directions of sigma and the principal stress values and principal stress directions of S. Now the reason I discuss this is because S, the deviatoric stress, is a very important quantity, especially when we talk about situations of solids or fluids where there is yielding happening, that is some sort of a plastic deformation. This tensor S becomes useful. So let's write the eigenvalue problem for sigma. So that's sigma ij minus the principal value, let's say sigma q delta ij, times an n hat q with j equals 0. So this is an eigenvalue problem for sigma. So these are eigenvalues of sigma, and these are eigendirections or eigenvectors of sigma. I can also say principal values and principal directions. Now I write my sigma as a sum of its spherical part and a deviatoric part, and minus sigma q delta ij times nqj equals 0. I'll combine these two. So this becomes an Sij plus a sigma m minus sigma q times delta ij times nqj equals 0. Now what I see here is that this actually is an eigenvalue problem for S. Should put double lines to show that they are tensors. So from this we can see that these are the eigenvalues of S, and these are the eigenvectors of S. So we notice that the eigenvalues SQs of S are simply the eigenvalues of sigma minus sigma m. We find the three eigenvalues of sigma and subtract sigma m from each, and you will get the eigenvalues of S. Again, we discuss this is because the eigenvalues or principal values are important because they help us with evaluating very useful quantities, especially in situations where we have plastic deformation happening in ductile solids or complex fluids such as non-Newtonian fluids. And we see that the principal directions of sigma are exactly the same as the principal directions of the deviatoric part, that is S. So as I mentioned earlier, that the spherical part is responsible for changing the volume of the body. In a similar fashion, I can say that the deviatoric part is responsible for changing the shape of the body. So I'll give you a problem to solve. We have to decompose this sigma into its spherical and deviatoric parts, and once you do that, you have to find the principal values of both the spherical parts and the deviatoric parts. We now move on to the last topic of today's discussion, that is on octahedral shear stress. So first we have to define the octahedral plane. So the definition of an octahedral plane is that it is that plane for which the normal n hat makes equal angles with the three principal directions of sigma. It's important that it has to be principal directions, not any directions. So you have to work in the principal coordinate system to be able to find or locate the octahedral plane. So with that logic, that means that n hat dot e1 star is the same as n hat dot e2 star is the same as n hat dot e3 star. That's saying that it makes equal angles. So the components of n hat, that is the octahedral normal, are the same in all three principal directions. So this will give us n hat as simply a constant times e1 star plus e2 star plus e3 star. And this constant is nothing but 1 upon root 3, because we have to ensure that n hat is indeed a unit normal, its magnitude has to be 1. So if I symmetrically place points A, B and C on the principal directions in the principal coordinate system, then the normal to this surface that we have of this symmetric tetrahedron is going to be the normal to the octahedral plane. So this plane, the shaded plane here, is indeed the octahedral plane. And the traction vector on this plane is going to be something like this. Of course, it need not be in the normal direction. And the traction vector here can be written as sigma star ij nj. Now sigma star is simply sigma I times delta ij. As we've been doing in the past, it's a diagonal matrix times nj. And when I expand that, this becomes 1 upon root 3 times sigma 1 E1 star plus sigma 2 E2 star plus sigma 3 E3 star. I can get sigma n as the dot product between the traction and the normal, which simplifies to sigma I Ni, which actually becomes 1/3 of the sum of sigma 1, sigma 2, and sigma 3. Again, I urge you to please check it yourself and confirm. And this is nothing but the sigma mean, which is 1/3 of the trace of sigma. And I can write my sigma s squared as Ti dotted with the Ti minus sigma n squared, which simplifies to this. So again, you should try it yourself to show that this is the expression for sigma s. It's an act in pure algebra to show this. And this sigma s on the octahedral plane is called the sigma octahedral, which is the octahedral shear stress. It's a very important quantity. In fact, it is related to the second invariant of S, that was our deviatoric stress part, like this. Again, I request you to try yourself and show this with the definition of the second invariant of S as we had shown earlier. So I'll remind you again, because many students and researchers make this mistake, that sigma octahedral depends on the octahedral plane, and the octahedral plane is defined with respect to the starred coordinates, that is with respect to the principal directions of sigma. So if you have any sigma given to you, that is sigma components in any coordinate axes, you first have to transform them into sigma star, work with x1 star, x2 star, x3 star, and then find the octahedral plane to get the octahedral shear stress. Now you may ask that why are we talking about this plane, octahedral plane? What is special about it? And there is indeed something very special about it. One is that it is symmetric. It is symmetric with respect to the three principal directions of sigma. So the principal directions of sigma are unique for sigma, which depends on the physical quantity sigma that we're talking about. So it's a plane which sort of is an equal balance between the three principal directions. Now, practically speaking, we have noticed that when we are studying yield criteria, that is when we start talking about plastic deformation of ductile wires, like if you take a wire and bend it, there is a situation where it will change its shape to the new shape, that is the process of yielding. And in fluids, we have complex fluids like ketchup, toothpaste, blood, or slurries of mud or snow. These materials, these complex fluids, they have a special behavior where they start yielding or flowing after the octahedral shear stress crosses a critical value. And this is a very important idea which we engineers or scientists have come across. That is, it is just through this one number, which is the value of sigma shear or sigma octahedral on the octahedral plane, we can figure out whether the situation is going to result in yielding or not. So if you had to do an experiment, you would find or measure sigma s on the octahedral plane in a given situation and check whether the sigma octahedral is greater than or less than a critical value to identify the fact whether yielding will happen in the situation or not. So it helps us fluid mechanicists to identify the rheology expression using octahedral shear stress value. So if the octahedral shear stress for the fluid at a given point is less than a critical value, it behaves like a solid. And if the octahedral shear stress is greater than critical value, it behaves more like a fluid. So instead of worrying about all possible planes and measuring things on that to identify yielding, we have a beautiful quantity called sigma octahedral, which we can measure or calculate and check for yielding. So since sigma octahedral, or the second invariant of the deviatoric part S, sometimes also called J2, where J2 is just the negative of the second invariant of S, they're all used in situations where we talk about yielding happening or not. In our research group, we work with snow avalanche dynamics, and snow avalanches, which are complex fluids flowing down the slope of a mountain, behave very much like complex fluids, and a mass of snow under a small shear would stay as a solid. But if the shear stress on the octahedral plane increases beyond a critical value, it starts to flow like a fluid, which becomes a dangerous situation. So the quantity octahedral shear stress is very useful for predicting the flow of avalanches on mountain slopes. So this brings us to the end of this lecture, and also to the end of our discussion on stress principles. We'll have a tutorial next, and then we'll move on to the next module, which is the third module on kinematics. So thank you, and I will see you in the next tutorial.